Yeah, hello everybody. First I want to thank for the invitation to give this talk and for the opportunity to give this talk here. I'm going to talk today about the role of African dust in in driving changes in the meridional overturning circulation applied to Heinrich events. And this is a work led by Lisa Murphy and myself and Amy Clement. They're both in the atmospheric science in the University of Miami. So first I'll give a quick introduction of what the Heinrich Stadials are. So these are millennial scale events associated generally with cooling and drying in the northern tropics. And here we can see in the plot on the left, the blue curve, the SST changes over time, going to the left, and then we see the Heinrich event, especially the Heinrich event 1, associated with the cooling of SST, and also changes in the ocean circulation, generally associated with the decrease of North Atlantic deep water, and these are associated also to the ice debris in the North Atlantic, and also is a time with a strong dust source, and we see here between 15 and 18, the Heinrich event 1, we see a strong dust source, about two and a half times what is present today, and this may have implications to the additional decrease of the AMOC in the ocean circulation. So here, the objective of this talk is to examine how the Saharan dust load during this Heinrich Stadial 1 could impact the climate, and especially the effect on the AMOC can be studied via heat and freshwater budgets, and also accounting for uncertainties in the wind forcing, dust, and freshwater forcing through hosing experiments. So for this, we use the University of Victoria Earth System Model, version 2.9. Is an intermediate complexity Earth System Model, so it has all the physical components, but it's the atmosphere. The ocean is the MOM2 in a coarse resolution, and the atmosphere is a one layer with some moisture advecture scheme, and yeah, so it has all the caveats associated with the coarse resolution model of intermediate complexity. And we analyze here 1,000-year runs simulations, and they are spun up for at least 3,000 years. And this is the good thing about this model: we can run long simulations. And to simulate the Heinrich Stadial events, we apply a forcing, forcing the North Atlantic between 45 and 65 north, and it's done via virtual flux of freshwater in the North Atlantic. And then we explore the wind in UVic. The wind is simulated as anomalies to the present day NSEP climatology, and via sea level pressure anomalies, and then it's calculated geostrophically. So this is the standard UVic wind that we use one of the experiments, and the other ensemble is doing with the Camp 4 sea level pressure anomalies, replacing the UVic anomalies and applying the same way geostrophically. So, and the good thing of the UVic is that it presents a hysteresis that we can study, especially in this kind of work. So UVic doesn't have a dust parameterization in it, so we had to implement it. So we implement dust via surface albedo changes, and the surface albedo changes for the shortwave radiation, and also we parameterize surface long-wave radiation and outgoing long-wave radiation, because dust it absorbs and emits radiation, so we need to simulate both effects. And so this parameterization is adjusted to the heat fluxes in the CAM model from Murphy et al. 2014, that they simulated the Heinrich event and this dust loading in the atmospheric model. So we try to simulate the same effect in UVic. And here is some of the parameters we tested, for example, to calculate the net heat fluxes. And so we have this H parameter here that we can scale the dust forcing. We can apply, like multiply by 1, by 2, by 3, so we can simulate this effect in the model as well. So just a quick overlook of the effect of the net radiation due to Saharan dust in UVic is about 6 watts per meter squared decrease in that region. And then we see in UVic generally a cooling of about 0.6 centigrades, and also a freshening in the North Atlantic due to both decreasing evaporation due to the cooling and also decreasing precipitation. So for the wind force, as I said, we use the CAM LGM winds and the UVic winds. Just a quick overlook here and compared to the NSAP winds. We see that the UVic winds generally it decreases the westerlies in both hemispheres, and the CAM it increases the westerlies there. So, and in the tropics, generally this approximation in the wind they are not very effective in changing the wind, especially in the tropics, more the extratropics. And then, so simulating the dust effect in the AMOC under these two winds, the UVic and the CAM winds that are strengthened in the westerlies. So we apply, first we have the control, the black lines, and if we apply the dust effect, and for different dust simulation, H equal to 1, 1.5, and 2, we have a decrease of the AMOC under UVic winds from the original 13 Sverdrup. So you have because you have a decrease in the westerlies, we have a decrease in the AMOC, so the mean is about 13 Sverdrups, and you have a decrease of about 20-25%, and just the increase of dust, just changing the timing of this variability, but all of them they simulate a 20-25% decrease. And interestingly, in the CAM winds, we have a much stronger AMOC, about 22 Sverdrups, so it's stronger than the present day AMOC, and the effect of dust is almost is negligible under dust equal to H equal to 1 and 2. So we try to understand these effects, and we try look at the difference between the UVic, the model under UVic winds and CAM winds. And you see UVic winds here on the top is the heat transport, meridional heat transport in the ocean. So we have, of course, with a weaker AMOC, we have a weaker meridional heat transport. And in green, when you have the dust, you have also a 25% decrease of this heat transport. And here you have the eddy variability is this dashed line is due to a Gent-McWilliams parameterization, which similar in both models, and is very small in comparison to the total. And you see the green and the black curves, they they're basically the same because we don't have too much AMOC variability under the cam winds. And here's the mainstream function also in the cam winds, stronger AMOC and goes further north and goes deeper, and in UVic wind is much shallower. And under dust, you have a strong, again, a stronger decrease, and under the cam winds, almost no decrease in the AMOC. So try to understand the heat fluxes, how they behave under the dust forcing. So we have in the first 100 years for UVic winds and cam winds, they're very similar. We have a shortwave decrease compensated by latent and long wave radiation, and mostly in the northern tropics in both models. And after, in the end, the last 100 years of the simulation, we have in the UVic winds a lot of changes here in the northern hemisphere, including shortwave decrease and compensated by latent and sensible heat, whereas in cam winds there are almost no change. And this could be explained here just quickly on the fact that the heat components, the long wave evaporation, sensible heat and short wave in the last 100 years for the UVic winds, where we have strong changes in the North Atlantic. And we see here the strong shortwave decrease in the Northern Hemisphere, and this is the dust forcing, and also we have this. And then we plot here on the top in the blue contour. This is the ice change. So we have ice accumulation here in the Northern Hemisphere, and then we have this effect in the shortwave. So we have this due to the decrease of the AMOC, we have a increase in ice as well. So to explain again the difference, we want to explain in terms of freshwater, different within the model, within the two simulations. So with the cam winds here on the left side, so we have both the ENET, the net evaporation integrated over the basin, is compensated by the ocean freshwater transport. Here is at the 34 south, so I have the net evaporate basin and positive MOV, so it imports fresh water, and this is have been studied, and this is what can be described as a monostable mean state, whereas in the UVic winds we have a negative MOV here, so it could be bistable effect here due to the export of fresh water. And this is important to understand when we're applying hosing. That is the simulation of the Heinrich events when you apply the hosing and the dust in the model. And you see, again, for the cam winds, we have a stable and a positive MOV. So we have so we apply the hosing for 200 years and shut off the hose after 200 years, and we have all the simulation for the different hoses, 0.1, 0.2, and 0.3 Sverdrups. We have all of them rebounding and recovering after the shut off after 200 years. And this for the UVic winds, we have both. We apply a much smaller freshwater forcing here, hosing the North Atlantic, and we see that some can recover here. First, the recovery is much slower in all of them, and it can, in this case here with freshwater 0.05, after we shut off, it just shut down the AMOC. And comparing by dust and for dust and no dust sources, so the dust are the solid lines, and we see that dust can delay for a couple decades the recovery of the AMOC, but not very different, especially in the CAM winds. Under the UVic winds that is more sensitive, we see that dust can have a strong effect and much more steep at the beginning here. And even though it's not much different from the others until you have a total recovery here that we have the 25% decrease. This is an interesting case here that I just want to point out here. In the one we have the dust, we can trigger a collapse of the AMOC wherever without the dust we have a return of the AMOC in this particular case here. So it depends on can be a triggering mechanism. And just to focus on this one, that is 0.03 freshwater force in the North Atlantic. I just want to give a quick example, and this can apply for the other runs too, but this is a good example to talk on why we have when you apply dust, you have we have a shut-off of the AMOC. And this also studying the MOV and the zonal freshwater transport. And this is the total, the sum of the two. So we see that, so these are anomalies relative to the control run. So with the freshwater minus control, and this is the total freshwater. And this for no dust, and the ones on the borders for with dust. And we see here, I want to point out just this this line, the blue line here, which is the MOV. So the MOV is negative, exporting fresh water, and then it goes close to zero, and then return to the same value when you don't have dust. And when you have dust, and then it can cross the line, zero line, and start importing fresh water. So this helps to make the AMOC more unstable. And you have in several cases the anomalies here. We have in most cases the MOV and the zonal component. They kind of balance each other until a certain point that the MOV dominates the ocean heat transport. So just a quick conclusion. We analyzed dust feedbacks in the Heinrich events and see the potential for changing the AMOC and changing the climate there. We see that the dust feedbacks can amplify these Heinrich events by cooling and freshening the North Atlantic. And we see two different behaviors of this. When the AMOC is bistable, it is when the MOV is negative, it's exporting fresh water. The dust can reduce the AMOC by about 25%, and even can trigger bifurcations as we see in this last event. And in a stable mode, when the MOV is positive, just may delay the recovery, but not very significantly. So this is a quick view of the work we have done here. Thank you.